And then Shane Boone with BDI is going to kick us off here.
Today I am going to talk about non-destructive evaluation of the West Seattle High Bridge, specifically the PT Ducts. So this structure, BDI was hired to do just the NDE portion. We worked with Dr. Mike Brown with regards to essentially evaluating the structure and identifying whether or not preservation needed to be maintained, or they needed to repair the structure, or even worst case, replace it. So I'll go through the NDE portion of it. First and foremost, we applied a multi-technology approach. So the idea here was to collect the right sets of data instead of just throwing one widget at it, for example, and then fusing those data sets so that we could give our client, who then gave Seattle DOT, the ability to make a data-driven decision. So essentially, what do we need to do with this structure? And I'll go through a little bit about what they were seeing with the structure exactly, and why these types of problems existed. And like I said, that way we were able to provide that useful data to the client. I'll go through the exact things that we did with regards to the PT Duct NDE, and then show how this multi-technology NDE approach kind of works for other elements as well. And then hopefully we'll have some time for closing. Multi-technology, essentially the idea here is, instead of just throwing one NDE at everything, so like, I think Jean knows this the best, is back in the 80s, everybody and their brother bought a GSSI antenna and said that GPR can detect delaminations on bridge decks. And it's been haunting my career the entire time because it doesn't do that. So identifying the right technology to evaluate the right element for the right degradation process is very important. And a lot of times, one technology doesn't do everything, right? So with NDE, that's very specific. NDE is very good at like very specific things. And if you're trying to evaluate a structure, you need to identify which technologies you want to deploy specifically for what you're trying to find. So we identify that multi-technology approach, and if you see this slide here, it's an old LTBP slide actually, talking about essentially as concrete degrades, what you're going through. And so, as you put rebar in an electrolytic compound, maybe we get a layer of zinc and we're happy, but most likely we're probably going to get some type of corrosion. That corrosion causes cross-section loss. That cross-section loss causes tensile cracks. Those tensile cracks cause spalls, right? So we can evaluate each one of those sections of the degradation process, but not just with one technology. So if we throw one technology at it, we're only getting one side of the story. And what we want to do is evaluate the entire story so that we can provide the information such that the client can make a data-driven decision. So once we do that, we deploy subject matter experts, not just any old technician that knows how to thump a hammer, but someone that actually knows about electromagnetical or electromechanical or electrochemical testing so that they know what they're looking at in the field. We combine and fuse those different data sets so they actually tell the entire story of the degradation process, the areas that are degraded, and the potential cause. And then we're able to present that information in a usable format such that the client can make that data-driven decision. So specifically for prestressed concrete, this is a pretty tough problem, right? When we're talking about post-tension duct, you've got a tendon that's encased in concrete, that's encased in a duct, that's encased in concrete, that's reinforced with rebar. So there's a lot of things to look at, right? And if you just threw GPR at it, maybe you just see a few things. Maybe if you just threw MIRA at it, maybe you see a few things. In this particular structure's case, there were all kinds of cracking. The client didn't necessarily know where they were coming from or what the potential cause was. Was it degradation of the tendon? Was it torsion of the entire bridge? Was it a design issue? And so going through this process of actually identifying the degradation cause through these different methodologies was what our goal was. Obviously, if the PT ducts were voided, that could be a huge issue. And so we deployed this multi-technology approach. We used UPV to detect how deep the cracks were that they were seeing. We validated that with ultrasonic tomography, otherwise known as MIRA. We did impact echo to further validate those findings. We did GPR to find where the ducts were, and then we worked with our clients to identify, okay, here's what we're seeing, what does this mean? And we also validated the results and took material samples. First and foremost, prior to us being brought on site, the specific structure had very large cracking going from the top flange of the structure down through the web and vice versa. And so essentially the idea was, okay, are we having an issue here with PT ducts? Is there potential Sika grout problems? Are the tendons corroded? Are we actually getting flexure of the structure itself because we're having loss of that pre-stress? Or is there another problem? And so we didn't know, so we needed to go through and find that data. You can see here that essentially the primary areas of degradation and the cracking was between the top flange interface and the web. And so our first methodology that we deployed was ultrasonic pulse velocity. We wanted to know, are these cracks through depth? Because on the visual inspection side of the story, they could see the crack on the inside and they could see the crack on the outside, but they had no idea if it went all the way through. So we wanted to determine if that crack went all the way through the web. So with ultrasonic pulse velocity, basically we're sending an acoustic wave from one sensor to another. So you got to imagine essentially if you've got two sensors on one place and there's no crack, the wave's just going to travel along and it's going to go from one sensor to the next, right? So you got a very clear time arrival. As that process and that cracking grows, the time takes longer. Once you get a full crack, maybe you get no response whatsoever. Okay, one methodology to test the cracks. With that methodology, we were able to identify that the majority of the cracks in the areas of suspicion were about at the rebar level. So essentially the crack grew to the top mat or the front mat in this case and stopped. But in some cases, it grew further. And so we wanted to go ahead and identify where those cases were and validate it further with another methodology. So in this case, we used ultrasonic tomography. And I wondered forever what MIRA stood for. Does anybody know? MIRA, not you, because I told you. Anybody else? So MIRA doesn't stand for anything, which in our industry of tons and tons of acronyms just confuses everybody. It just means see in Spanish. So you're seeing through the concrete. And what you're doing is you're essentially sending lots of ultrasonic waves through the material at the same time and creating this three-dimensional image. So one line of these sensors will fire, the other 40 will listen, and so on and so forth. And it uses this process to essentially make a map, a 3D map. So back in the day before we had GPS on our cell phones, remember when it would triangulate where we were? That's what MIRA does, except it's doing with acoustic waves in concrete. So we're able to do that, and we basically did it from right above the web. Okay, so we know that that's where the cracks are across the web interface between the top flange and the web. So we ran MIRA essentially right across that top web interface on the top flange on the top of the deck to validate the ultrasonic pulse velocity results and identify that yes, most of these results do end up with cracks that are just to the depth of that front mat. And so, okay, that's what we wanted to see. We want to make sure that we don't have through crack depths. And then, so we took all that data, so it's in a usable format, and said, okay, if we just provide a histogram and a bunch of dots, that's probably not going to be very useful for the client. That's just a squiggly line. And as engineers, we don't like to see squiggly lines. As structural health monitoring folks like Tom over there, he'll be like, oh, I like squiggly lines. But we don't want squiggly lines. We want usable data. So we took that data and essentially said, okay, let's create it in a usable format, a presentable format, so that we can look at it really quickly and say, okay, where are these cracks? How deep are they? Do we need to be concerned? From that data, we were able to identify, okay, here are cracks that are potentially through the web or deeper, and we're concerned about those. Let's go ahead and expand upon that and identify where the ducts are in that region that could potentially be a concern, and let's scan them. This is where GPR comes into hand. GPR is very good at finding metallic objects. So in this example, you can see on the top side that you're seeing all the front mat rebar. In this case, we used, instead of a single frequency GPR, we used what's known as a continuous wave step frequency GPR. So you're able to actually look across multiple frequencies to ensure that you're seeing the second reflection as clearly as you're seeing the first one. So a lot of you have probably seen GPR records. Usually you see that top mat that's very clear, and the second's kind of fuzzy. We don't want that. We want to look at multiple frequencies simultaneously to be able to see clear results from all of the depths. And using this, we can identify where that top or front mat is, and then we can subsequently identify where that middle PT duct is. And that's where we want to drill, because we don't want to drill through bar, and we want to hit the duct if we're going to excavate and validate our results. So using this methodology of continuous wave step frequency, we're able to identify exactly where the ducts are and where we want to inspect them. And then we can go back to our UPV and MIRA and say, okay, here's where a duct is, here's where a deep crack is, I want to inspect that one. All right, so now we've used 2 or 3 methodologies and we've identified which ducts we want to inspect and how we want to inspect them. So from there, we're going to essentially look at the cross section, look at, okay, this duct is essentially supposed to be vertical, but it's harped a little bit. So we want to take that into account when we're looking at these, because we're going to get a weird reflection from that middle part, because potentially a lot of those tendons are sucked up into that vertical harp, and take that into account. So we're going to bring back ultrasonic tomography, and we're going to use it once we know where the ducts are to inspect them. Ultrasonic tomography, like I said before, is essentially a way to send multiple acoustic waves through a media and listen for that response and get a 3D result. And from that, you've got to imagine if you've got a duct that's intact and then you've got a void inside it, that's a difference of what's called an acoustical impedance. That impedance is essentially like you're yelling at an echo. So if you're screaming across a mountain and you get a mountain that's right here versus a mountain that's right there, you're going to get a reflection from the first mountain first, right? So you might hear 2 echoes. If you only have 1 mountain, you're going to hear 1 echo. So if you've got a back wall with a nice intact duct, you're just going to get 1 echo, right? 1 mountain. If you've got a voided duct, that's another source of air, just like your back wall, it's like 2 mountains. You're going to get 2 echoes now. And so that's what we're looking for. We're looking for those voided ducts. And so with MIRA, we're able to send a lot of acoustic waves into the media and look for those voided ducts. And so you see on the right-hand side of the slide there, those are areas on the back wall. We're getting a nice clean reflection from lots of air. In the middle, we don't want to see much reflection, but in this particular case, we are. So we're worried about 3 areas of this specific duct. And then we're going to get a little bit from the top mat of rebar as well, because it's a different type of density material. The rebar is obviously stiffer than concrete, so we get a reflection from that as well. We don't want to use one technology. So impact echo is another acoustic technique. A lot of people are more familiar with impact echo than MIRA, but essentially it's just one sensor of MIRA. So we're sending a single acoustic wave, and don't think of it as a laser. It is conical. It's like when you drop a pebble in water, everything moves. So you're not just getting a single, laser pointer right back at me. You're getting some type of weird reflection. So it's important to take lots of data sets, and that's the same way with why we're comparing these different technologies. And so same way with MIRA, we moved right along where we knew the duct was from our GPR result, and we expect a very clean back wall. Why? Because the wave will move through a consistent media to that mountain and right back to us, unless there's another mountain, i.e. void, in between. When there are voids, we can see them. Okay, we get multiple reflections, we get slower waves, we get some type of degradation of that acoustic signal that indicates to us that there's a potential indication there that could be a void. And then per NCHRP 1428, which investigated this type of technology and these type of multi-technology approaches, we take those 2 data sets and we fuse them together to ensure that everywhere that we're looking is going to be spot on if we're going to drill into a PT duct, right? We don't want to do that if we absolutely don't have to. So in the case of this specific project, we wanted to identify A, if there were voids, B, if there were voids, if the steel tendons were starting to corrode, and see what was the corrosion mechanism, or what was the degradation mechanism. Was it something to do with the grout? Was it lack of consolidation? Was there bleeding during the pumping process such that you had areas of wet and soft grout that would potentially cause degradation of that tendon? And so using these different techniques, all of them together now, we're able to identify, okay, where's our crack? Where's a tendon? What's the voided potential in that tendon? And then use a bore scope and investigate it. So we've used all these different NDE techniques to arrive at a decision of where do we actually drill, because we don't want to drill unless we have to. And then at that point, we worked with the client to essentially identify, okay, we've got all these positions, we're going to drill, we're going to see what's going on there, and we're going to take some samples. And specifically, we found voids. We found a lot of voids. We were able to take material samples. Material samples came back really well, relatively. The cross-section loss of the tendons was simply not there. And so from our perspective, it may have been a QA/QC issue. And then we were able to take that data, give it to our client, who could then proceed with identifying what the best process for retrofit, repair, or replacement of the structure was. Taking material samples, we also wanted to know if there was potential chloride ingression due to the fact that this was over a brackish water area. So we also took material samples of the concrete fascia itself just to make sure that we weren't getting corrosion of the concrete itself and not the duct, and potentially that was what was causing cracking. So to kind of loop all that back in, now we have all of these data sets, and what do we do with it? Well, we worked with our client daily to essentially identify what our testing schedule was and what those results were. So where do we want to test next? Do we want to continue with the path that we're on? What is the analysis showing? Are we seeing that everything is voided? Are we seeing that nothing is voided? How do we proceed? Where do we want to drill? Do we want to drill? So do we want to take material samples, and what are we seeing? And so that all led on a daily basis for a couple months on, okay, we've taken all this test. Now we're going to deliver this final report to our client that essentially is identifying the depth and location of cracks, whether or not they should be of concern, i.e. whether or not they're through the full web depth, where the ducts are that we found that could have potential voids, and did we excavate them based on our client's recommendation? If we excavated them, what did we find? And putting all that together so that our client could put that information into an engineering decision that could provide the owner with the ability to determine whether or not this was a choice for preservation, repair, or replacement. And so the end result ended up being a retrofit, but it saved the owner hundreds of millions of dollars essentially, because our cost was peanuts to test a very large portion of the bridge to identify where those voided ducts were and what the degradation mechanism was, and the fact that the degradation mechanism wasn't leading to cross-section loss of the tendons, and thus the tendons were in good shape. And so by doing this type of multi-technology approach and approaching it specifically for what you're looking for, you can use NDE to identify exactly what you want to find, hopefully, in most cases, not always exactly because it is somewhat subjective, but you can use those results to allow the owner the information that allows for a data-driven decision. And so that's really what we want to talk about. And so ultimately, I was talking to Tom earlier about this. When I come to these conferences, I always am interested in the fact that I am listening to a presentation that has to do with preservation and what preservation activities are being done to a structure. And I'm always very curious, hey, if we'd have been involved, or not even BDI, but just if NDE or monitoring had been involved prior to that preservation activity, what would have changed with that decision? Would have it been the same, or would have it been slightly different because there was more information to be used to make that decision on how to preserve or maintain the structure? Obviously, this isn't just for cross-segmental box girders. We've done it on T-bulbs, PT duct structures that aren't just cross-segmental, bridge decks, unknown foundations, and substructures. You can take this process and essentially move it towards any type of investigation that you want to do, as long as you're following that process of identifying what you really want to determine and what technology you need to use to make that determination, instead of just throwing one widget at everything. Thank you.
The preceding was produced by the National Center for Pavement Preservation. More information can be found on the web at pavementpreservation.org. Additional support provided by Michigan State University.